So with the high spin, we have a set of 3. So 3 into, so that's 3 pi e's. And I'll subtract those out because they're negative. And we've also got a set of 2. So we've got a total of 4 pi e's. What do we have here in the low spin? So we've got 3 up-pointing electrons, which is 3 pi e's, and we have 2 down-pointing electrons, which is also subtracting 4 pi e's. So the pi e's in this case don't tell us anything. It's all a battle between the value of delta O and the value of pi c. That tells us which spin state would be expected. There's a chart on page 382 that lists all the options for, what have we got there? Weak field arrangement on the top. So this is the high spin on the top, and the low spin, the strong field arrangement on the bottom. And then at the end of the strong field arrangement, we have what the difference is. So you notice on 5d electrons in the d5 state, 2 delta O's and 2 pi c's is the difference. Minus 2 delta O's and plus 2 pi c's. That's what we just derived here. So in the middle of that bottom half, we get the differences. D1, D0 through D1, or D3, there's no difference between, well, there is no options. They are the same. So the differences only matter for D4 through D7. How do we figure out the value of delta O? Now we've sort of dealt with pi c's. It depends on the diffuseness and the size of the orbital. A small tight orbital has a large value of pi c, but an S6 or 6s orbital, big, diffuse, very expanded, pi c value goes down. So pi c depends a whole lot on the size, the physical size and diffuseness of the orbital. So we can't really say what the value is. But we do want to have at least a chance of saying what the delta O value is. What techniques do we have?
Absorption.
Absorbance. Look at the absorbance peak. Shine white light in it and see what color is absorbed. There's a slight problem with using absorbance. If you look at absorbance here versus wavelength, those peaks are really wide. So this would be 400 nanometers over here and 650 over here. You're looking at really wide peaks. You can still find the top. And you can say, okay, there's the top, that's what the value is. But because these molecules are not standing still, they're vibrating all the time, bonds are lengthening, bonds are shortening, bonds are changing their angles. What it means is this arrangement is not rigid. The whole thing is going up and down. Certain orbitals are dropping while others are going up. So often, instead of having this arrangement, it's really an arrangement that looks more like that. And we're looking at all kinds of excitations from one of these to one of these, and that just broadens the peak like that. So we're dealing with a broad peak. We call the top, and we're just happy with that. We can't do really much better. Let's see, I need a table.
Would emission at 90 degrees in the sample be better, so you don't have like all the background difference? Or is that really
No, that's what you're talking about there is fluorescence. And these do not, or these very, very rarely de-excite through fluorescence. They say de-excite photonically. They don't, once you have an electron in an excited state, they almost always find a vibrational method of getting back down to the ground state. Very few of them. Gold is one example that does. You can get gold with a wide variety of ligands, and it will de-excite photonically, so it will fluoresce. But most of them won't. Okay, so on page 380, we have an idea for aqueous ions only of what the values of delta O and pi C, or I guess this is the combination of pi E and pi C, have. Well, it's mostly pi C. For different transition metals. So these are the hexaaqueous, hexaaqua states. And you notice vanadium that has a really big delta O and that tends to go pretty stable. The numbers aren't changing a whole lot for those +2 ions. What about +3? What's happening to delta O? It's getting bigger. It's actually kind of opposite what you would anticipate. So if we were looking at the ligand, well, the ligand field theory model of how that 3 down, 2 up came about. We had 6 bonding orbitals down here. The T2G non-bonding set was here. And the EG anti-bonding set, here's the EG bonding set, was there. So if you had this diagram for 3D, what would change if you took away 1 electron? Because that's what we're seeing here. We're going from 2+ to 3+. Take away 1 electron, what is changing? That helps. Take away 1 electron from the metal, what changes? Why is delta O getting bigger? What's the only way to make delta O bigger? Well, 2 ways. What are the 2 ways to make delta O bigger?
Does it open up a spot on our lowest, on our iron triple?
No, because all of these electrons came from the ligands. I'm not taking the electron from where the ligands are.
So it's only
So
the
all
non-bonding.
these 12 electrons, they occupy these. By taking away an extra electron, I'm not changing those. I'm not deoccupying them.
So that's it, drops.
Okay, I can drop this entire set of d orbitals to a new lower position, which means the T2Gs come out lower. What can I do to lower what can I do to lower the overall electron energy of the metal?
Down.
I take away an electron, what happens? Why do these electrons drop in energy? Z effective went up. That's what happened. So that's what we're seeing there. We're seeing the increase of Z effectiveness, or Z effective, and so the T2G set is lowering down. The EG anti-bonding set's probably staying where it was. So you make something more and more ionic, make it more highly charged, and delta O is going to get bigger and bigger. Well, what do you think of this new delta O versus the old one? Delta O prime, it's now bigger, significantly bigger. Yes.
I want to go back. You're saying that the non-bonding set will go down. Wouldn't the anti-bonding EG also drop? If you're lowering this whole set of
They do.
d orbitals,
They do. These will go down, but because you haven't changed these, they're holding these up, where these didn't have anything holding them up. So yes, these also go down to a new position, but these have not changed. And so they're helping hold these up. But that had nothing holding it up. It drops fully. So what do you think of the spin state of 3+ transition metals? Spin state. So the question here is, with this delta O, by changing the ligands, we were changing from high spin to low spin back and forth. With this new big delta O, what's going to happen? Low spin. Low spin dominates. So when you look at the spectrochemical series, it really applies only to the 2+ transition metal ions. When you get to the 3+ and the 4+, low spin is ruling everything there. So just anticipate low spin. There are some examples. There are some 3+ ions with the right kind of ligands that will be high spin. That happens. But for the most part, you can make some plans. And you also notice in that table, again, page 380, the pi values are many times bigger than the delta O values. So the delta O values, what that means is you need a pretty significant value of ligand field stabilization energy. You need this to be 2 or 3 delta O's before it's equal to the pi values for most cases. So can we take a single metal and a single set of ligands and predict ahead of time what the value of delta O will be, or what the spin state will be? Which ones are we most sure of? 2+, well, 3+, we're probably going to be low spin. We're not going to know the value of delta O. 2+, we can use the spectrochemical series to help make up our minds, but it gets really tricky in the middle. So if I've got carbon monoxide, I'm pretty sure it's going to be strong field, low spin state. If I've got halogen ion, pretty sure it's going to be weak field, high spin state. But in the middle, there's a big guess. If I take a hexaamine ion of a 2+ transition metal, I don't know. I don't know what it's going to be. Make it and look at the color. See if it's yellow or red. See if it's on the red end of the spectrum or the blue end. That's the only way really you can start to tell. Okay, let me see. There's one other thing I wanted to talk about, and I don't think it's in this chapter. Kind of some extra rules. What do you think happens when you go down a row? Oh, here we are. I'm on page 396. Or, well, I'm moving past page 396. No, that's not it. Well, that's getting to what I'm trying to get at. What happens when you move to the second transition metal row? Do you think? What do you mean?
Like, as you move down, you start to get low spin with the halogens and high spin. So it's hard